Okay, in this next section, 10.2, Summing Infinite Series, we are going to talk about what it means to be an infinite series. So you should have already seen and be familiar with this notation from Calc 1 when you talked about Riemann sums and how we defined the definite integral via the limit of Riemann sums. But as a quick refresher here, this notation is summation notation, or I guess some may call it sigma notation, since this is the Greek the Greek letter capital sigma. So really, what goes here is going to be some expression, and it defines a variable, or called an index. So this is oftentimes called the index of the sum. But really, this word index could as equally as well be called variable. But we're going to call this index. So this is the index of the sum, the variable of the sum. It gives the initial value, or starting value, of the index. And then up here, this infinity tells us the final or stopping value. And then this right here is the actual expression. It's the expression, it's the rule of the sum. So what will happen here is each one of these terms of the sum, the first term of the sum, the second term, the third term, we are going to plug in each value of the index, starting with 1, going all the way to infinity. We're going to plug in each number into this expression and evaluate it. So when we plug in 1, we get 2 times 1, and that's why there's a 2 here. And then when we go to the next term of the sum, we increment or increase our index to the next whole number, which is 2. It plugs 2 in here, so we have 2 times 2, which is 4. Plus, we go to the next index, which is 3. 2 times 3 is 6. Plus, so on and so forth, all the way to infinity. That's what a sum does. We have seen in Calc 1 where this had sometimes we had a finite, concrete, real number as a stopping value, whereas other times in Calc 1 you may have seen an arbitrary number here, some capital N, and then we used a limit as this capital N goes to infinity to make the sum that looks something like this turn into something that looks like that. All right. So for definition 1, it is an nth partial sum. So the nth partial sum of a series is defined as sort of an estimation. Instead of going from whatever your initial value is, in this case some arbitrary number k, and going all the way to infinity, a partial sum is exactly what the name suggests. It's an incomplete sum. We're going to only go so far, because going all the way to infinity could be difficult or time-consuming, but if we just go to some finite number, no matter how small or large, it can be accomplished in finite time. So this nth partial sum here, what's really important, and is a very common misconception, is this is the stopping value of the index, which is exactly what we said a moment ago when we were reviewing summation notation. But with partial sums, it's oftentimes forgotten. So before we go down here to these examples, we'll do a quick example off to the side here in blue. So if I give you a series, let's say from, I don't know, n equals 5 to infinity, so there's an infinite series, and my rule is maybe, I don't know, n squared. And I ask, I ask for, so given this series, find S sub 8. A very common misconception, and and it's very common, we see this a lot, is that students will, or first-time learners, will assume that this notation S sub 8 means add up the first 8 terms of the series. So find the first 8 terms. So this is incorrect. This is incorrect. We always start with whatever the initial value is listed as. So instead of actually starting with let's say 5 squared, 6 squared, 7 squared, 8 squared, 9 squared, 10 squared, 11 squared, 12 squared, this goes all the way up to the 8 terms, 1, 2, 3, 4, 5, 6, 7, 8 terms. This really, S sub 8, if we follow the definition, and this is why definitions are important in mathematics, is you want to make sure that you are actually using and understanding what is intended by this notation. So by definition, this notation means the sum from whatever the initial value was before, but instead of going all the way to infinity, we're going to stop at 8. So this means actually 5 squared plus 6 squared plus 7 squared plus 8 squared. So all those terms down here that were erroneously included can really throw off your answer. So remember, this subscript here, the partial sum, only tells you how far to go, not how many terms are actually present in your sum. In this case, because our starting value is 5, that means in order to start at 5 and go to 8, we'd have to do 1, 2, 3, 4 additions. So be careful. A very common misconception. Okay, so example 1, the nth partial sum. Calculate these partial sums. So find S4 given this series. So again, by definition, S4 is the sum from our starting value of 1 in this case to 4 of 2n. So this is 2 times 1 plus 2 times 2 plus 2 times 3 plus 2 times 4. So 2 plus 4 plus 6 plus 8. So we have 10 and 10, so 20. S2. By definition, S2 is the sum from n equals 0, in this case, the starting value, to 2. 1 over 2 raised to the nth power. So this is 1 over 2 to the 0 plus 1 over 2 to the 1 plus 1 over 2 squared, or 2 to the 2. So this is 1 over 1, which is 1, plus a half, plus a quarter. So this is 4 plus 2 is 6, plus 1 is 7. This is, 7 fourths. Okay, taking a look at example 2, here we're going to abstract a little bit, and we're going to take a look at the same series from example 1, part 2, and we're going to determine the first 4 partial sums. So, S0 is the sum from n equals 0 to 0, 1 over 2 to the n. So the only thing that we get, is 1 over 2 to the 0, which is 1. The next partial sum is from n equals 0 to 1, 1 over 2 to the n, which is 1 over 2 to the 0 plus 1 over 2 to the 1, which is 1 plus a half, which is 3 halves. So notice here, This next partial sum is just the previous partial sum plus the next term of the series. So S2, the sum from n equals 0 to 2 of 1 over 2 to the n, it should be, I'll write it down here, this should be equal to the previous term, the previous partial sum of 3 halves, plus the next term that we're including, so the n equals 2 term, which would be 1 over 2 to the 2. So this is 3 halves plus a quarter, which would be 7 quarters. So let's see, does this check out? 1 over 2 to the 0 plus 1 over 2 to the 1 plus 1 over 2 squared. And you can even see just by association here, this right here is exactly that. So this we know is 3 halves. So that does work out. Sometimes it's useful and quicker to think of it like that. It's less writing out. There you go. So then the next term, we're asked to calculate the first 4 partial sums. So S3. Again, this doesn't mean the first 4 partial sums. This doesn't mean go up until you have S4. This means start with whatever your first partial sum is, whatever n value that may be. In this case, since our sum began at 0, the first partial sum is the 0 term. So 1, 2, 3, 4. So be very careful. The language here is very important. So S3 is the sum from n equals 0 to 3, 1 over 2 to the n, which we just argued a moment ago is going to be equal to our previous partial sum. Let's call this S2 plus the term that we're omitting, that we are now including, the n equals 3 term. So this would be 1 over 2 to the 3. So this is 7 fourths plus 1/8. We need a common denominator here, so this is 15 eighths. So now what I want to do is take a look at a sequence. So below in this remark, if you list out the successive partial sums, that list in and of itself, in its own right, is its own sequence. So given any series, you can create a new sequence from them. This sequence would be the sequence of partial sums. So far, we've created a new sequence, S sub n, where the first term is 1, the next term is 3 halves, next term is 7 fourths, and the next term is 15 eighths. So if you had to wager a guess, what would S sub n be in general? So again, it's sometimes useful to think of this. This is the 0 term, first term, second term, third term. And then can you come up with a formula or an expression? This ends up being, notice that the denominator is just 2 to the n. 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, 2 cubed is 8. So the denominator is definitely 2 to the n. But the numerator is always 1 less than the denominator doubled. So for instance, 8. If I take 8 and I multiply it by 2, I get 16. If I take 1 away from 16, I get 15. Same thing here. 4 times 2 minus 1 is 8 minus 1, which is 7. So the numerator is 2 times the denominator minus 1. This sequence of partial sums is exceptionally important when it comes to defining what it means for an infinite sum to converge. What does that mean? We know what convergence of a sequence means, but what do we mean when we say that an infinite series or an infinite sum converges? Which we'll talk about in the next video.